You've probably heard someone say, the normal distribution is everywhere. Well, that's almost true. Human height, almost normal. IQ scores, close to normal. Measurement errors, usually normal, but not everything follows this famous curve. So today, let's understand why it's so special. Let's look at completely different kinds of data. Student heights, exam marks, manufacturing measurements, sensor readings. At first, they seem unrelated. But when we plot enough observations, a familiar shape keeps appearing, the famous bell curve. So what is this curve actually telling us? It's showing how common different values are. Notice where most people are standing, near the center. That's where the most common values live. Now look toward the edges. Fewer and fewer observations appear. Those values are much rarer. The normal distribution says something surprisingly simple. Average values are common, extreme values are rare. Every normal distribution has a center. That center is the mean. In a normal distribution, the mean sits exactly at the highest point of the curve. And here's something beautiful. The left side is a mirror image of the right. That means the distribution is perfectly symmetric. If you fold it down the middle, both sides line up exactly. That's one of the defining features of the normal distribution, perfect symmetry. But why does nature create this shape so often? Imagine throwing darts. Most throws land fairly close to the center. Only a few are extremely accurate or extremely inaccurate. That's because many tiny factors combine together: your aim, your grip, your balance, the wind, your reaction time. Each tiny effect adds a little randomness. Together, they naturally produce a bell-shaped pattern. Whenever many small random effects combine, the normal distribution often appears. This is one reason the normal distribution is everywhere in AI. Camera sensors introduce random noise. Measurements contain tiny errors. Machine learning models make prediction errors. Many of these quantities are approximately normally distributed. Understanding this curve helps us understand confidence intervals, z-scores, and anomaly detection. But there's a hidden secret inside this curve. 3 simple numbers, 1 sigma, 2 sigma, and 3 sigma, can tell us almost everything about our data. We found the center of the normal distribution, the mean, but knowing only the average isn't enough. We also want to know how spread out the data is. That's where standard deviation comes back. One standard deviation, or sigma, is simply a measure of distance from the mean. The farther sigma reaches, the wider the bell curve becomes. Now here's one of the most famous rules in all of statistics. If your data follows a normal distribution, about 68% of all observations fall within 1 standard deviation of the mean. Expand just a little farther, to 2 standard deviations, and suddenly you've covered about 95% of the data. Go out to 3 standard deviations, and you've covered 99.7% of all observations. Only a tiny fraction remain in the tails. Let's solve a simple example. Suppose human height follows a normal distribution. The average height is 170 centimeters. The standard deviation is 10 centimeters. What percentage of people have heights between 160 and 180 centimeters? Notice, this interval is exactly 1 standard deviation on either side of the mean. And from the 68, 95, 99.7 rule, we already know the answer, approximately 68%. That's why this rule is so... What about observations far away from the mean? Those are called outliers. Because only 0.3% of the data lies beyond 3 standard deviations, finding values this far away is unusual. Sometimes they're perfectly valid. Sometimes they indicate something went wrong. Either way, they deserve attention. Why do AI engineers care? Imagine monitoring bank transactions. Most purchases follow normal spending patterns. But suddenly, one transaction appears far outside the usual range. That unusual point becomes a candidate for fraud detection. The same idea powers anomaly detection, quality control, and sensor monitoring. The bell curve helps AI recognize when something doesn't look normal. Let's summarize. The mean sits at the center. Sigma measures spread. About 68% lies within 1 sigma. About 95% lies within 2. About 99.7% lies within 3. Values far outside are rare. If data follows a normal distribution, approximately what percentage lies within 1 standard deviation? 68%. What about within 2 standard deviations? 95%. True or false? Most observations in a normal distribution lie near the mean? True. true. Remember this sentence: 1 sigma catches most, 2 sigma catches almost all, 3 sigma catches nearly everything. Here's something incredible. Even if your original data isn't normally distributed, the averages of many random samples often are. This surprising result is called the central limit theorem, one of the most important ideas in all of statistics and machine learning. We'll uncover it next time.